And in this case, we discuss the carrier synchronization and symbol synchronization for coherent detection. And by definition, synchronization is the process of making coherent detection possible and then maintaining it throughout the reception of the digitally modulated signal with minimal or optimum error performance or minimal error. There is optimal error performance or minimal error at the receiver. And in ideal situation, coherent detection requires an exact replica of the received signal so that we are able to synchronize the transmitted bit with the received bit. It implies that the receiver has complete knowledge of the phase of the carrier signal that was used at the transmitter. And in such a case, the receiver is said to be phase locked. So I believe you have seen us discuss this. We're talking about we have a receiver, a transmitter here, and at the transmitter we have a carrier with a given phase, and this is the TX, this is the RX. So here we are modulating the carrier signal with our message bit of a combination of bit stream of ones and zeros, and here we are receiving a carrier that is phase modulated. So at the receiver, we want to know what was the phase at what instant of the carrier that the transmitter, and therefore when we are able to estimate the phase at the transmitter, we can be able to know if this was the phase before it was modulated, what is the message that was sent so that it changed the phase of the carrier signal. So we normally try to identify the phase of unmodulated carrier at the transmitter. That is the idea. So if we're able to do that, and in ideal situation, we can say that we have locked the phase of the transmitter with that of the receiver. So coherent detection is performed by correlating the possible incoming signal with one of its replica, and the decision is made based on comparison of the threshold levels. So for instance, I just want to draw, this is the carrier signal at the transmitter and at the receiver. So I want to time them. If this is what we have, but then we are realizing that at the receiver we are having a phase that is, or a signal that is out of phase by 180 degrees phase shift, then we can know that this 180 degrees, if it was sent for BPSK, represents a bit 1. And in the presence that there is no phase shift, then we are able to identify that this is 0. So for instance, this one, if it follows that of this is at the TX, this is at RX. So this is out of phase by 180 degrees, whereas this one is in phase by, and therefore there is 0 degrees phase shift. For that reason, we can be able to identify that this was bit 1, if 1 represents 180 degrees phase shift, and this is bit 0 for a BPSK signal. So that is the essential purpose of carrier synchronization. We are trying to estimate what was the carrier signal at the transmitter and compare that with the one that is received at the receiver. And once we're able to get the phase of the transmitted carrier, then we are able to know how much change in phase has been caused, and therefore what is the likely cause of that change. So there are two methods of synchronization. One of them is carrier synchronization, and the other one is symbol synchronization. And for carrier synchronization, we see that knowledge of frequency as well as the phase of the carrier is required, and when those two are available, we consider that to be carrier signal recovery or carrier synchronization. That is the other name that we use for carrier synchronization. That is carrier signal recovery. And for the symbol synchronization, the receiver has to know the instance of time. This is also called timing synchronization because we are looking at the instant at which the given symbol has been or is appearing in the modulated signal. Therefore, we say that the instant at which the modulation occurs, and we sample that is the one that we refer to as the symbol synchronization. So, for instance, in this example I've given, assume we know that the bit or the symbol starts at instant t is equals to 0. The other symbol instant happens at t is equals to ts. And the other instant that change that happens is at t is equals to 2ts. If you're able to estimate the times when the symbol has changed, then that kind of synchronization is the one that is referred to as symbol synchronization or clock signal recovery. These two methods can occur either coincident with each other or sequentially one after another, and there are different methods of achieving either of these. But before that, we say that cardiac synchronization or cardiac signal recovery is primarily used, is the most commonly used method of synchronization for coherent detection, and cardiac synchronization is of no concern for, we don't require cardiac synchronization when we are doing non-coherent detection. Therefore, it is primarily used for when we are doing coherent demodulation of a digital signal. So there are a number of methods that are used. One of them is empty power. We are not going to go into the details, but at your own time you can be able to look at these two and find out how they are used to implement the cardiac synchronization.